Hi, my name is Tarek Diaa Eldeen. I am a BRU21 PhD candidate in engineering cybernetics. My project is called History Matching and Closed Loop Reservoir Management, and it's sponsored by Equinor. So, the closed loop reservoir management is a model-based feedback optimization procedure that aims at optimizing the overall production process. So as we can see here, the production starts with some highly uncertain models that are obtained from the geological data, such as seismic tests and well logs. Then, as the production starts, we use the actual measurements to update those models and characterize the uncertainty. However, the main challenge here is the high dimensionality of the reservoir models and also the scarcity of the observations in the actual field. So this leads to an undetermined model updating problem. So any introduced improvements in updating the initial geological models can lead to great economical benefits. So there are two classes of solutions that can be introduced to tackle this ill-bosedness problem. The first class is the variational methods, where the estimation process is cast as an optimization problem, and we can use regularization or reparameterization or sampling to handle the ill-bosedness. The other class is the iterative statistical methods, mainly the Ensemble Kanban filter, which is a Monte Carlo implementation for the standard Kanban filter. Also, this depends on sampling. And in both approaches, the sample initiation is crucial for the accuracy of the estimation of the reservoir fields. So this figure illustrates the basic idea for the Ensemble Kanban filter, where we choose some samples to represent this initial probability distribution. Then we propagate those samples and approximate the propagated uncertainty from the ensemble itself instead of the full distribution. And originally, those samples are selected randomly. So what we have proposed is to consider the system's observability in selecting those samples instead of selecting them randomly, as this might lead to enhancements in both estimation and optimization of the process. So observability simply is the ability to measure the internal states of the system from the actual observations. The main idea is that if we can choose the initial ensemble members in the directions that maximize the observability of the system, then this might lead to some improvements. In addition, this also guarantees that the perturbations will be orthogonal, and this will reduce the redundancy within the samples and also can lead to computational efficiency. The main challenge here is that the observability analysis is not straightforward in the case of the multi-phase heterogeneous reservoirs due to the high nonlinearity. For example, we need to compute the sensitivities with respect to both dynamic and static variables of the whole reservoir. So this was implementing using automatic differentiation as the simulation is running. Here we show some results from applying this technique. So here we have an initial ensemble mean for the random sampling, and here for the observability-based sampling, and this is the actual permeability field. And those are the updated fields for both cases. Then we computed the estimation errors for 10 different random cases. And for the observability-based case, we can see that the mean for the random cases was approximately 0.23, and with a minimum of 0.16. And in the observability-based method, we obtained an error of approximately or even less than 0.15, which is lower than the minimum value in the random cases. If you want to know more about this, you can read our papers. Thank you for your attention.